Hello, hello. This week's fiddler is, I thought it was a bit tricky. I'm not really that good at geometry, so it's not really my forte here. And so I'm not quite confident that I have the right answer, at least to the extra credit. So if you find the better solution, please go ahead and post that in the comments. But for now, let's get into the question, which is suppose I have a bunch of 3 by 3 tiles and 5 by 5 tiles. I want to know what's the smallest square I can possibly make where I have this constraint that I have to use at least one of each type of tile. So I can't just put one 3 by 3 tile down and say, look, size 3 square. If you're feeling really cheeky, put no tiles down and say, look, a 0 by 0 square. That's not allowed. You need at least one of each. And so what's the best we can do? And the problem, of course, is that 5 and 3 don't play nicely together. They're what's called relatively prime, meaning they have no factors in common. And so it's very hard to stack 3 by 3 tiles and 5 by 5 tiles in a way that makes anything like a flush edge. So the only method that I really could find, which I'm calling method 1 here, but it's the only one I could find, is essentially to stack 5 3 by 3s or 3 5 by 5s next to each other. And so you get a stack like this, where the 5 by 5s, the bigger ones on the right here, I have 3 of them side by side, and then the smaller ones, the 3 by 3s, stack like that into a nice height 15 rectangle. Now, I think you could probably do something a little more complicated than this, but it would eventually essentially boil down to this in like a torus is a coffee cup kind of thing. But anyway, using that logic, I can create an 18 by 18 square, right? So if I have this 5 by 5 and 3 by 3 stack, I can do it vertically and horizontally here, and then I've got a little bit extra that I do. I put a little extra 3 by 3 square there, and this gives me an 18 by 18 square. Now I think this is the best I can do, but I tried playing around with some digital tiles to see if I could make the square even smaller. I could not, which doesn't mean it's not possible. I certainly don't have a proof that you can't do smaller. So if you find something smaller, let me know. But there are a couple things that I thought about what possible candidates I could use. So the first thing to think about is that any square, if it's size x for the side, then it needs to have two equations with positive integer solutions. The first is the edge length has to be equal to the sum of 3 times some positive integer a plus 5 times some positive integer b. This is essentially reflecting the fact that if you think about, for example, look here, the bottom edge of this square, right? The bottom edge is going to be made up of some length of 3 by 3 tiles and 5 by 5 tiles. And so whatever number I use here, it's going to be a bunch of 3 by 3s, a bunch of 5 by 5s next to each other. And so, 3 times however many 3 by 3s there are in that row, plus 5 times however many 5 by 5s there are in that row has to equal the side length. So that's the first consideration. The second is that if I think about all the 3 by 3 tiles I use and all the 5 by 5 tiles I use, their areas have to add up to the area of the square, which is x squared. So I need to satisfy those two equations. Obviously, a, b, c, and d can all be different, but I need to be able to satisfy those with positive integer values for a, b, c, and d. So the only numbers I could find that satisfy that are 14, 16, and 17. And I played around again trying to make squares of those sizes. I couldn't do it. Again, does not mean it can't be done. I couldn't do it. If you can do it, let me know. Or if you found another number I missed that satisfies these equations, also let me know. But again, the problem is how do I actually make a square with that smaller size? And I think the reason this breaks down is if I think about this first equation, or one way to think about why this breaks down, why I couldn't make it out of these, is there's only one way to make 3a plus 5b equals 16, even if you allow 0 in some spots. Whereas with 18, right, I have 3 5s and 1 3, or I have 0 5s and 6 3s. Right, so there's two different ways I can do it. And so what that means is different rows can have different layouts of squares. And so I could possibly do something to make that work there. Whereas when there's only one way to do it, I think that really limits the ability to make a square. So that's just one way to potentially intuit why that doesn't work. Or you can just think about the fact that to get those flush edges, I think you really do need 5 3s and 3 5s. I think basically without doing something really large, that's the only way to do it. So moving on to the extra credit. Now I'm going to have a bunch of odd length tiles. They're all size 3 or larger. So, and I have as many as I want. And that's of 3 by 3s, 5 by 5s, 7 by 7s, 9 by 9s, so on and so on. And the question is, so importantly here, I'm allowed to use 0 of a particular type of tile. So I can use for 9 by 9s, I can say I'm using none of those, none of the 11 by 11s, none of the 13 by 13s, etc. So I'm allowed to use 0 of any type. And the question is, what's the largest square where I cannot make that size square using these odd length tiles? So that is the challenge. What's the smallest square, or sorry, the largest square you can't make? And the first thing I'm going to do is kind of note something, and then we're going to reframe the problem. So the first thing to note is any square that's not a power of 2 fairly trivially can be made into this square. So what do I do? So I'm going to divide whatever number I have by 2 until I get an odd number. Now, importantly, that odd number is not going to be 1, because if it's not a power of 2, that means its prime factorization is going to be a bunch of 2's, potentially. It might be no 2's, but it might have some 2's, and then some other number, some other prime number that's not 2. And so if I divide by 2 until I get an odd number, I'm basically going to get the prime factorization without the 2's, which will not be 1, because there has to be another prime in there somewhere since it's not a power of 2. So, so given that, now I have that odd number. I have the tile of that size because I have every odd number more than 1. So I'm only going to use those, and I can make the square using only those tiles. And basically I stack them, 2 to the power of how many times I divide by 2 to get there. So as an example, suppose I pick the number arbitrarily, 68, divide by 2 to get 34, divide by 2 to get 17. Okay, so I can use 17 by 17 tiles. How do I make a square of size 68? Well, I divided by 2 twice. So I'm going to have to stack them in a 4 by 4 pattern where each of these purple squares is a 17 by 17 tile, and that's going to give me a 68 by 68 square. So, so any number that's not a power of 2, I can basically do this exact method and create the square. The problem is, what is the power of 2? How do I make a square of size power 2 at all? And so the way I kind of reframe this problem is, what's the smallest square whose side length is the power of 2 that you can make using these odd length tiles? Or not 1. So I can't only use one type of tile, right? I have to use at least 2 types of tile. Why is that? So it's because if I have some tile of length x and I have some positive integer n, if I multiply those together, I'm never going to end up with a power of 2 because again, thinking about the prime factorization, x is an odd number, so I'm never going to end up with n is an integer. It's not, and it's not 0. So I'm never going to end up with power of 2. So how am I going to do this with 2 tiles? Well, if I have 2 types of tiles, and if they're relatively prime, I'm just going to use this x by y tiling like I did with the 5 by 3 example and align them. If they're not relatively prime, you could do a little better, and we'll talk about that a little bit in a second. But again, just to drive home this point, I really tried using some digital tiles to figure out some way to make tiles that are relatively prime form a flush edge without using that XY method, and I just couldn't do it. Again, it doesn't mean it can't be done. I don't have a proof that's the only way to do it, or at least that's the only way to do it with relatively small size. You could effectively, you could do something potentially, I don't know that you actually can, where this gets quite large and like loops around into a square. But I don't know if you could even do that. So, but I think effectively for the purpose of this problem, I'm going to think about this assuming that you have all these XY edges. So as an example, suppose I want to make a 15 by 8 rectangle, right? We do it like this with 5 3s and 3 5s, and that works. Now, can I make this into a power of 2 side length square? Well, 8 seems to be promising because 8's a factor of any power of 2 is at least 8, right? If it were 64, that's just 8 8s. And so I could stack them that way to make a power of 2. But 15 is not, and that's bad because if I stack, it doesn't matter how many times I stack it. If I stack 15 on 15 on 15 on 15, I'm never going to get to a power of 2 for the same reason, right? This is an n times x problem. I've already got a non-power of 2 in there. I can multiply it by whatever I want. I'm not getting rid of those prime. I'm not getting rid of that 5 and 3 in the prime factorization. So I'm never going to get to a power of 2. So in order to make this work, I would essentially need another rectangle that also had length 8 on one of its sides, but a different height from 15. And then hopefully I could stack these together in such a way that I could end up with a power of 2. So that is one way to approach this. Unfortunately, there's just no other way with the tiles that I have to make an 8. So we're going to not do that. But 16, which is the next power of 2, there are lots of ways to make that. So I could do 3 and 13. I could do 2 3s and 2 5s. I could do 5 and 11. I could do 7 and 3 3s. Now, importantly, I'm doing 7 and 3 3s instead of 7 and 9 because you end up with an easier way to, or a more compact way to stack them. And so if I have 3 and 13, again, I'm going to do this 3 times 13. That's going to have size 39. The 3 and 5 one, this might not be super intuitive, but because I have 3s and 5s, I can stack basically the 3 and 5 next to each other. And then the other 3, to the left of the first 3 and the other 5 to the right of the first 5. And so I really only need a height 15 to make that 3 3 5 5 work. Same thing, 5 and 11 make 55. With the same thing with 7 and 3, I can do 21. And this is why I didn't do 7 times 9, because then I would need size 63. But just to show you the example, if I have 7 and 3, I only need 3 7s, and then I can do each of the 3s next to each other. And that will still give me, length 16, right? 7, 3, 3, 3, that's 16. But the height here is 21. So that works great. And then the question is, I want to find the smallest power of 2 such that there are non-negative integer solutions to, I guess non-negative is not right. Oh, sorry, no, non-negative is right here. To this equation where x is my power of 2. These are the sizes of the rectangles I can make, and then I'm using some integer, it could be 0, of those squares. And the smallest I could find for this is 256. Maybe there are others, and actually there are multiple ways to do it. One of the ways is no 15s, 421s, 339s, and 155. I can't remember the others off the top of my head. There was one that I think used no 55s, maybe 8 of something else. I don't know, but there are at least 3 solutions that I found to this setup. But they still had 256 as the smallest base. I couldn't get smaller than that using this setup. So that's going to create a 256 by 16 rectangle, which I can stack 16 times side by side to make a 256 square. Is this the smallest? I don't know. I'm not convinced that it is. I think the only way you could really prove this is to do some kind of exhaustive search, which I certainly did not do. And the reason that I'm a little bit skeptical of this answer is, well, first of all, I chose 16 as kind of the smallest power of 2 where I get multiple rectangles out of it. But since I end up getting to 256, there's no reason I should be stuck with 16, right? I could try 32, lots of different ways to make 32. And you may end up being able to get something smaller than 256 from those components. It seems perfectly plausible to me. I just didn't even try it. And further, you don't even have to use power of 2 as the other side, right? In the same way that you can stack rectangles vertically of different sizes, you could stack rectangles horizontally of different sizes and get kind of look to try to get to the same width as height using different stacking methods. That's another way to do it. So there are definitely, I could definitely imagine ways that you could make a smaller square. I just didn't have the time to really investigate thoroughly how to go about it. So if you do have the time and want to let me know how to find a smaller square than the one I found, I'd be very interested to hear it. So anyway, thanks for watching and have a good week. I'll see you next time. Bye.